So this is a topic about related rates. It's again another applications of derivative of a function. But these questions, these topics is somehow quite demanding in the sense that it requires you to be able to translate a physical scenario into the language of mathematics. In particular, you are given some kind of scenario like the one given in the examples, and you're supposed to be able to relate the physical quantities in the questions and translate the scenario as described in this physical system into the expressions that mathematically describes the change of such physical system. So generally, you are given some kind of geometry. So the geometry given in some problem would change in time or would change in some of the variable in it. So when one of these variables changes, such as the time changes, then the geometry in the questions will change. So you should be able to write down an equation that relates the change in the time, for example, into the change in, say, the height of a physical system or the speed of how a balloon rises. Okay, so as I mentioned earlier on, some times ago, there are three types of questions in physics which could be ranked according to the level of cognitive understanding. So the simplest level is a question where you are given some formula and you are asked to apply the formula straightforward and then just reproduce the answer. So this is a very low level kind of direct learning process. So in that case, you just have to blindly apply formula and then get your answer straightforwardly without much thinking. The second level of complication is this kind of questions where you are given a physical system without any formula. The questions is describing to you a scenario. So its descriptions is all in the language of English. So you have to understand the scenario and then able to understand what is changing, then extract out the physical quantity, then represent it with a symbol, then relate this symbol with a differential equations. So it's an applications problem, which is considered as the sort of like a more difficult question than the first level question where you are just asked to use a formula to calculate some straightforward quantity. Right, so this is the second level of difficulty in terms of mathematical questions. The highest one would be a questions where it requires you to relate different topics, different concepts that you learn from different, say, different subject or different topics in more general situations, more different. Say, for example, you learn about series, then you learn about algebra. Then the question requires you to combine the concept from both algebra and from the series into a single question. So you have to be able, in that case, to recall what you learned from different aspects and then put that onto the same questions. So that kind of questions is considered as the most difficult one. But here we are dealing with a physical scenario questions. So you need to first understand the questions very correctly. If you fail to understand the questions, then it will not be possible for you to translate the questions into the mathematics. So you need to say first, as I mentioned, understand the questions, then extract out the physical quantities that are involved in the system, then write down an equations in terms of dy dx or some geometrical relationship that relates this quantity. Then the next thing would be to solve the equations that you write down. So in this case, the equation are not given to you, but you're supposed to write down the equations. Right? So if you fail to understand the questions, if you fail to understand the translations, if you fail to translate the problem into equations, then it will not be possible to solve the equations. Then it will not be possible for you to answer the question. So it comes in three stages, right? Understand the whole situations, translate the scenario into mathematical equations. Then the third one is to solve it numerically. So solving the equation is the most easiest part. is the easiest part in the in this process, right? So let us try to tackle this problem one by one. I'm going to discuss two examples here. So here you have a tank, and the tank is a vertical cylinder. It's a vertical cylinder. So it is quite important to realize that you have a vertical cylinder. Okay. So you need to understand then what you mean by a vertical cylinder. You need to know what is the formula that describes the volume of a vertical cylinder. So this requires you to recall the fundamental mathematics that you learn in your, Form 2 or Form 3. Like in Form 2, Form 3, you learn maybe Form 4 in the worst, the volumes of a cylinder of some geometrical shape. You must be able to know that information. That is the volume of the formula for the cylinder. V is just equals to the height of the cylinder multiplied, what I would say, the height of the cylinder multiplied with the area of the cylinder, which is written as pi. So this refers to the cross-sectional area of the cylinder. Height means the height of the cylinder. But here in these questions, you have actually two kinds of height. First is the height of the cylinder, which is a fixed number, and also the height of the water that is contained inside the cylinder. So you have a cylinder containing a fluid, presumably some kind of water. Then it has original volume of that much. Right? It has a original volume of that much. Then you opened a tap. Then the tap will start to drain away the water. So when water is drained out, it is drained at a rate. So you have to be able to understand that in terms of mathematics, when the water gets drained out from the cylinder, that would cause the volume of the cylinder to decrease at a rate. Right? So it could decrease fast or decrease low, but we do not know how fast it is. But we expect that the volume as a function of time initially is some number, initially at V0, for example, then it would get smaller and smaller as time passes by. Right? At any time of states, at some time t prime, for example, then the rate of change of the volume is just given by dv dt. So in this case, you have to understand that the rate of change of a volume of cylinder is due to the draining of the water from the cylinder tank, and the rate of change is just the slope of the V versus T graph. And then you need to find out what is, well, if so the volume of the water or the fuel or the fluid inside the cylinder is decreasing at some rate. So generally, the rate is described by dv dt. Right? So the rate could be positive, could be negative. If the rate is positive, that dv dt is positive, it means the volume is increasing. If dv dt is negative, that means the volume is decreasing. So in this case, it is obvious that the volume is decreasing. So you have a rate that is running out at a constant rate, which is minus 3,000 liters per minute. So this is the questions. You have to understand what you mean by the drain. The water is draining at the rate given by this. Okay. So then you also need to know how the volume of the water is written down in terms of the height of the water level and in terms of the radius of the water. So here the question requires you to identify a few quantity, namely the radius of the cylinder and also the height of the water level. So these two will give you the volume of the water that's still contained inside the cylinder, and the volume of the water is decreasing at a rate which is given by dv dt. So dv dt is how the volume is being drained out at the rate. Okay. Now at this time also you have to understand that the volume is also dependent very much on h, right? So the h is a height, but the height will also change because the volume is changing, right? So if you draw out the functions, then you expect the volume to decrease, so is the height to decrease. Now how is the height h changes as a function of time? So you have to figure out how, right? So the volume is dependent on the height through a simple relationship. So this is the volume of the water as I write it down, and pi r squared times h. So here the symbol V refers to the volume that is currently contained inside the cylinder. H is the corresponding height, right? So when V change as a function of time, so is height will change as a function of time. So you can imagine that when water starts to drain, the height will change as a function of time. And so is the volume of water. Well, let me write it like this. When I write it like this, this is what I mean. V is the volume of the water, is a function of time. That is, when time changes, then the volume will change. And also, this volume also depends on the values of H. Right? So time changes, volume change, then the height. Sorry, when time changes, the height will change. When height change, then since volume is dependent on height, so the height is also changed. So what you recognize this, right? So it means the function of the volume is dependent on H and H depends on T. So you can then understand that this is like composite function, right? The volume of the water is a composite function which depend on the values of the height. So now you ask a very simple questions, how to relate the change in the volume and the change in height and the rate of change of this volume and height in terms of time, right? So time, rate of change of height, rate of change of volume with respect to height, they are all related. So their relationship could be easily extracted if you understand the logical relationship between the volume and the height and the time. So volume depends on height, height depends on time. So if you look at this aspect, then volume is like a function of height, height is a function of time. So then the rate of change of the volume with respect to time is then could be just written down by using what we call the chain rule. Remember the chain rule say it is then dv dt is just volume depend on height, and so is height depend on the volume. Okay, so this should be dh dt, right? Dh dt. So so the volume change is a product of how the v depend on h and how h depend on t. As I mentioned earlier on in the previous slide, the volume depend on the cross-sectional area pi r squared times height. So from here it is easily written down the dependence of h by v. So I say the v contain h, right? When h change, then dv dt describe how v depend on h. So h is changing, then dv dt will change by just equals to pi r squared. Now in this case, it has to be understood that r in this case is a cross-sectional area is a constant, but it doesn't change. So if it doesn't change, then there's no variation in the cross-section, right? So you look at the volume, when it drops in the height, the cross-sectional area R remains a constant and is not changing. So when you take the variations of volume, you only attribute the variation in volume as due to the change in the height, and the volume does not depend on the cross-section. Right? The cross-section is being constant when it drops. In more general situations, you can have the change in volume due to the change in height as well as change in the cross-section area. For example, if you talk about, say, not a cylindrical tank, but say a cone, right? So if it's a cone, then the change in height happens to cause a change in volume. And when volume change, also the cross-section area of the water will also change. So that would become slightly more complicated. But in our case here, the change in volume is simply due to a change in the height. So if you have a linear dependence of h by v, then dv dt is just dv dh. So we have dv dh equals to pi r, which is a constant. Then you could then easily simplify this relationship. Let me knock off this and then rewrite my equations here. So from here, the change of height as a function of time can then be just simply equals to just dv dt, which is the rate of change of volume with respect to time divided by dv dh. So dv dh is nothing but just your pi r squared, where r is a cross-sectional area. So you look at the question. The question says, I know the volume is being depleted at the rate of minus 3,000 liter per minute. And then there's a cross-sectional area of r, but I do not know what is r. So I think in here it is not mentioned what is the volume of r. So let me look at the solutions. Yeah, so this is what is mentioned here, right? So dH dt is just the ratio of dV dt over dH dt. So here dV dt is pi r squared, which is not known, r is not known. But anyway, we can still write down the expression for dH dt in terms of dV dt. And dV dt here is a constant, is minus 3,000 liter per meter. So I'm just going to rewrite these equations in another slide, which will say now we have these expressions of dH dt equals to minus dV dt, which is minus 3,000 liter per minute. So this is a unit of dH dt, then is divided by pi r squared. Pi, and you have r squared. So the question now is, what is dH dt? The question is not given. So we have to try to slot in the values of r equals to 1 meter and r at 10 meter and see what the answer is. Before you get the exact numerical answer for dH dt, so for r equals to 1 meter and r equals to 10 meter, you must expect that finally your answer of dH dt has to be in the right sign and has to have the correct unit. So we will have to show the unit correctly and the sign correctly. So the sign is negative for sure. Then you have to show that finally the dH dt has to be in the unit of meter per second. Here, the unit is not shown properly, it's liter per minute. So you have to combine L per R squared and minutes into the unit of liter per second. Okay, so how do you do that? Just proceed on. Just look at the basic knowledge from your physics. Right. So 1 liter is well, maybe not 1 liter. 1 liter is 1 kilogram of water, right? So 1,000 liter corresponds to 1,000 kilogram of water, and 1,000 kilogram of water has the size of 1 ton. 1 ton of water is 1,000 meter cube. So 1 liter, no, I think this is not right. So 1 liter is 1 kilogram of water. So 1 liter is 1 kilogram of water. So we have to somehow relate the liter to the meter, liter to meter. How do we relate meter to liter? So let us think. So 1,000 liter of water is 1 ton. 1 ton of water is 1,000 kilogram. 1,000 of kilogram of water has how many cube? How many cubic? So I think it is 1 kilogram of water, 1 meter cube. So somehow we have to relate the liter to a meter cube. This is the correct statement. I think this is not right. So I have to think about it a little bit. 1,000 liter is equals to 1 meter cube, right? So this is a basic relationship. 1 meter cube of water is 1,000 kilogram. 1,000 kilogram is 1 ton, right? So 1,000 kilogram of water has the volume of 1 meter cube, and then 1 kilogram of water is 1 liter of water. So 1 kilogram of water corresponds to 1 liter of water. So 1,000 kilogram of water is 1,000 liter, is equals to 1 meter cube of water. So this is a relationship between the liter and meter. So once we have done that, then we can proceed to the next part. Okay, so here we have to say if R equals to 1 meter. So 1 meter is slotted into the equations. So let's see what it is. So it is equals to negative 3,000 divided by pi, and you have to be careful when you slot in the number. So we have to slot in the number together with the unit. So 1 meter is just 1 meter squared, right? So you have 1 meter squared here. So let me just write it in a more clean manner, which is just equals to 1 meter squared. Okay, so that comes from r equals to 1 meter, slot into the expressions of r squared. Then you have to look at the liter. So you have to express the liter in unit of meter. So 1000 liter is 1 milliliter. So therefore 1000 liter is 1 meter cube. So 1 liter is 10 to the power minus 3 meter cube. Okay, so that is the relationship that you will slot in to liter. So 1 liter is 10 to the power of minus 3 meter cube. So that is the values for liter. Right? So 1 liter is 10 to the power minus 3 meter cube. Then you have to divide the meter, the minutes into second. Right? So if you need it into second, you just divide it by second. If not, then you just retain it as minute. I think whether you express your DHCT in terms of meter per minute or meter per second, it doesn't really matter. It's not necessary that you have to express it into second. But if you want to, you can. But maybe for the purpose of consistency's sake, I just leave the unit of time in minute instead of express in terms of second. If you want to, then you just convert minute to second by just a factor of 60, right? So 1 minute is 60. So I'll retain the minute here like this. Okay, so then we are almost done, right? So here this is equals to so this is 3000. You have 3 factor, then you just cancel off this one. You have a 3 over pi minus 3 pi, then you have meter cube, meter squared. So this we cancel off. You have meter per minute. So if r is equals to 1 meter, the change in height is just equals to minus 3 over pi in unit of meter per minute. Okay, so it's just conversion. But if r is equals to 1000, then you can easily do the answer by just factoring in the factor of, instead of 1 meter, you put it into 10 meter. Then here downstairs you have a factor of 100 in the denominator. Then your number will be slightly different. Okay, so you do it for yourself, but the answer is all specified in here. Okay, so you can't see properly because my iPad is not sure, but if you refer to the note, this will give you the correct number. Okay, so this is expressed in units of meter per minute. Okay, so this is another questions. Example 2. Now again, this is a question that requires you to translate the scenario into the equations that relates the quantities in the scenario. So you need to understand the scenario, you need to understand how to do the translations, and then write down the equations, then solve it. So a hot air balloon rising straight up from a level of field in a truck is tracked by a rangefinder 500 feet from the lift-off point. So this is a scenario. You have a balloon somewhere at some point, and the point is at the distance of x away from a reference point. So this is x is the lift-off point. So you track the lift-off point from the rangefinder. So here is a rangefinder. This is the point where the balloon is released. So when you first read the questions, then the first thing you would do is to draw a vertical line to mark down 2 quantities on your figure: the point where the rangefinder is and the point where the balloon is rising. So these are the 2 marks, and then the distance between them is symbolized by the values of x, and here the x is remain as a constant, right? So the balloon will be released when t equals to 0. The balloon is located here. When t is allowed to run, the time start to click, then the balloon will start rising, right? So at some time t later, the height of the balloon is called h. So this is the height of the balloon, then you label the height as h. So you need to know how to translate this scenario, right? So you mark down the point on the vertical line representing 2 points, or one for the rangefinder, one for the balloon. Then you imagine the balloon is rising, and the height of the balloon from the ground level is labeled by a label of H. Right? So if you are able to do that, that means you are being able to translate the questions in they translate the scenario from the question into a graphical forms for us the first time. Then when you have finished translating the scenario into graphical form, then you translate into equations form. Right? It's always easier to write down the questions in forms of a graph of a picture. Only then you translate the picture into equation. That is usually what we do for this kind of question. So imagine when you look at this scenario, the height is changing. Right? The height is changing. Then you imagine you draw a line. Right? You draw a line. Let me draw a line with a different color from the height, from the ranger point, from a rangefinder point to the balloon. Then you have an angle. So the question say this is the angle that is defining the height of the balloon from the viewpoint of the ranger. So here the height and the theta, the angle, are actually correlated, right? So the height and the tangent and the theta, they are two different measures that describes the positions of the balloon, right? So you can describe the position of the balloon from the above the level in terms of H or in terms of theta. They are more or less telling you the same thing. It's just that one is in H, one is in theta. Now in physics, this is very often used in mathematics also. Same quantity that's changing, you either express the changing quantity in terms of A or in terms of B. But these A and B, they are related to each other. Here, H and the tangent theta and the theta are related, but they are related in a way which is not so straightforward. So we are going to continue with this and to write down an equations that will relate the variable H and the theta, right? So, so the question asks you, at the moment when the theta is equals to pi over 4, then it tells you that the rate of the increment in theta is 0.14 radian per minute. So the question asks you, in that case, then what is the height? What is the rate of the height? How fast is the balloon rising at that moment? When that question is asked, you are supposed to be able to understand that when you say fast, you are actually asking a rate. What is the rate of height change when theta is measured to be 0.14? So in these sort of questions, you don't really measure the height of the balloon directly. You measure the angle, right? It's easy to measure the angle using some kind of a range finder. So it's kind of a measurement. You can easily measure the angle, but you don't really measure the height. So, but you can infer the height from the angle. So the measure of height and so the height is measured in terms of angle. So now you have to then realize how you would relate all these quantities. So what quantity are there? You have H, you have theta, you have X, and also have a time at the background. Then you have already translated all your scenario into a pictorial form, and you have identified what is your variable X, theta, H. Then the next thing you want to do is to write down the formula. Now, I think the questions here, the height is not written as H, but it's written in terms of Y. So I better call this Y. Okay. So now let us try to see what kind of quantity you need to write down. The quantity you need to write down is to relate the height Y to the angle. So obviously, if you understand the triangle method that we have already mentioned long time ago. So if you have angle, which is like T, and this is a X, then this is Y, then the Y, T and X, YT and theta is simply related as Y is equals to tangent theta multiplied with X. Right? So this is a straightforward formula that you write down that require that translate that describes the geometry of the problem. Then the next thing is that you have to relate how the Y is changed when theta changes. Right? So you can imagine that theta changes as a function of time. Right? So when time changes, the angle just increasing. So in that sense, then you can view the values of theta, a value of height to depend on the angle. And the angle instead depends on time. So then the height of the balloon from the ground level is then seen as a function of theta, and theta is a function of time. So y, that is a height, is now considered as a composite function, right? So then you can apply the chain rule to the composite function. That is the change of height with respect to time in y will be just equals to dy d theta and then d theta dt. So d theta dt is the rate of change of angle with respect to time. Y dy dt is the rate of change of height. Then dy d theta is just a derivative of y with respect to t, which basically relates the geometry of height and angle. So easily dy dt, dy d theta, let me write it with a different color. So dy d theta is just equals to secant square theta, right? So the d dx of tangent x is secant square x. So here it's very important to understand that when you look at the scenario here, the x, which is the distance between the rangefinder and the point where the balloon is released, is remain a constant. So x, even though it's x, but you should understand that it is a constant. So x is a constant, so it remains a constant and it's not dependent on theta. So dy d theta would assume that x is just a constant. So that is how you got this number. So dy d theta is this, then d theta dt, dy d theta is x secant square theta, dy d theta is just a rate of change of the angle at certain value. So you just put in the number, right? So when theta is equal to pi over 4, then it is said that at this angle, then the dy d theta dt is 0.14. Right? So here we know what this is and we know what this is. Then you just slot in the value. Then you get the answer quite straightforwardly. So here is the answer, I think here. So the dy dt is this. Then d theta dt is 0.14 and theta is a pi over 4. So you slot in this number into the equations that is being described here. Then you get the answer quite straightforwardly. So the answer is shown here. It is 150 feet per meter. So again, it is an illustration of the applications of the rate of change for a composite function. Now, again, if you look back at the way how we solve the questions, finally, when you get this number, it is actually not that important whether it's 140 or 150, 101.1. Number is actually not that important. The important is, do you know the process of translations and the process of calculation? So if you were be able to write down your answer step by steps, like what is shown in the slides here, then you'll be able to answer it correctly. Let's first look at the scenario, translate scenario into geometric form, then work out the dy dx, then put it into equations, then only you solve it, right? So in the previous topics, usually you are given some formula, then you just apply the formula without needing to explain it. But for these kind of questions, you need to know how to interpret the questions in order to get the correct answer, right? So you need to have an extra steps of thinking. So the questions does not give you the equation directly. You have to derive this equation yourself. Right? In the previous case, the equation is given to you, so you don't need to derive it. Here, you have to come up with your own equation. So in the exercise, there are quite numbers of such kind of related rates questions. So you can try to check out if you understand this concept or not. I personally find that this is actually not as difficult. Okay, so that's all for this lecture.